this series of lectures with two main themes. The first one for the first hour will be what I promised for so long, which is the definition of rough integrals and some of their properties and simple things. And then the last hour will be devoted to the study of a nice example of rough path, which is somehow unrelated to the rest. It's a nice example where you can do some explicit multiplication and see what is going on, and it's almost relevant for physics. So just to motivate, I think I explained last time that in fact, so our aim is, as usual, we would like to define the rough integral, let's say from A to B, of something because this is a rough integral, I want to denote it by a boldface x, and I said last time that I wanted to define this using definition, which is, as you can imagine. So what we are going to do is look at first order. And so we shall naively, I repeat it again because, but why not? So we shall say that this is essentially f of xa xb minus xa plus f prime of xa, and then I would see a double integral somehow, and this double integral I'm going to replace by its rough path version and subdivide. So, which means that in fact, I'm going to associate this to gamma st, which is f of xs, xt minus xs. I'm just repeating, plus f prime of s x ab, and then I will introduce rough Riemann sums. And so essentially, if I have a subdivision, a tagged subdivision, which will be A equals T0 less than or equal T1 blah 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 less than or equal T2n equals B, I will define as usual. So my notation for that is maybe a bit too complicated, but let's, what did I choose? In fact, the letter I chose, I just want to make sure. So R delta, and I will indicate a certain number of things here, and it's going to be here the sum of m plus 1 to m plus 2 minus gamma t to m plus 1 equals 0.
Would you slightly lower the blackboard?
Yes. Okay, so that was, well, okay, so that's what we are going to do basically, but we would like to make something just slightly more general. First of all, because most of the time I've been sticking to one dimensions, but for the manipulations we are going to do, it's not totally obvious how they would generalize to a multidimensional setting. So I will write explicitly tensor products and all that in what follows. to see how things go. For you see, this lives in a tensor product, and then it's important to know where things hit on the tensor product, and also.
Michel, I think it should be ST in the indices of blackboard X. MIC.
Yes. Agreed. Thank you. And then if we go to that, maybe I should also add the parenthesis. So before doing that, I would just like to observe, make a small observation. Is that's something we are not totally used to think about when you think about Riemann integrals or even the big integrals. I don't know exactly, but the point is the following: that in fact, when we define the Young integral, we didn't define this for Young integral. In fact, if you look at the notes, there are some comments on what you can do with this. So you try to integrate a function of xs against xs. But what we did was, in fact, we went to something more general, which was ys dxs. So somehow we decided to loosen the relationship between the integrator and the integrand. Somehow, well, of course, they needed to have some joint regularity, which means that if this one was beta Hölder and this one alpha Hölder, alpha plus beta had to be strictly larger than 1. But apart from that, the integrand and the integrator were completely independent. And if you think about it for Brownian motion, for instance, in stochastic integrals, there is a similar situation that, in fact, you can integrate things which are not at all functionals of Brownian motion or in a very, very indirect way. That's Ito integral, similarly. Ito does much more than integral f of bs dbs. You can really do something, you can really use things much more general than that. It's usually this thing here is going to be a complicated functional Brownian motion, but it can depend on all the past and all that. So it can be rather nasty somehow. Okay, so, and we would like to do a step forward this situation also for half path, and the situation for half path is a little bit less good, but you can nevertheless, at a low price, generalize a little bit. And this leads us to definition. We are going to do something which is a bit better. We are better than just f of x. And this leads us to the notion of controlled half path. And I already said a few sentences about it, but and the idea is the following. So you imagine, I will reinstate some tensor products here. So let me do it gently. I will, as usual, be totally silent about topology. I will indicate norms and all that in tensor products. Just imagine they've been chosen properly and don't ask me what they really mean. But they exist. So we imagine that we have an AB to F, and these are just vector spaces and Banach spaces, in fact. And now you imagine that X is alpha Hölder. So for that, you need a norm. That's okay. Well, that's not too complicated. So let's mention nevertheless that there is a norm E. There is a norm F. Imagine that X is alpha Hölder, and you define, this is definition, you say that Y is controlled by X if I will give a precise definition. Local fluctuations of Y are of order let's say those of X. And the precise definition is the following, is that you are going to write yt minus ys minus something I call y prime s xt minus xs. There is a y prime such that you have this here should be of order t minus s to the 2 alpha. Okay. So you see this is of order t minus s to the alpha. So this has to be as well of order t minus s to the alpha, and because of this structure, indeed, when xt minus xs is very small, this one has to be very small. Okay. Locally, the fluctuations of y are controlled by pose of x, and I would just like to mention that y prime s, for each given s, it belongs, in fact, to the continuous maps from E to F. Am I correct? E to F, yes. So you see, this here is an endomorphism, and this, it takes an element of E and takes it into an element of F. So indeed, these things live in the same space. And it is also natural, as one demands moreover, that y prime be alpha Hölder. And in fact, you see, the point is that if you interchange x and y and take the difference, this equation implies that in fact, when you take y prime s, y prime t minus y prime s xt minus xs, this should be of order, this is of order t minus s to the 2 alpha. And of course, this could be possible even if this is alpha Hölder. If this is alpha Hölder, then we're done. So this is a sufficient condition. This is not a necessary condition because this one could be much smaller, and then this one could be bigger. But we need some uniformity in things, and so the mathematical definition is that this guy should be an endomorphism, and the dependence on S should be alpha Hölder. Okay. So, right. Okay, so then there is some vocabulary. So, y prime is called a control of y by x, and y prime is called the Gubinelli derivative of y with respect to x.
Michel, is there a unicity quite natural?
No.
No.
Okay,
So
so
you can really write dy is equal to y prime dx.
I'm sorry?
Dy is y prime dx more or less.
Yes.
Y prime is not unique.
Well, okay, so it depends. So the point is, so suppose x is in fact better than alpha. We have defined it with a certain exponent alpha, but if x is alpha Hölder on a compact interval, it can also be 2. If it's 2 alpha Hölder, it's also alpha Hölder. So imagine that now, suppose x is 2 alpha Hölder, y prime equals any Hölder, object is okay. Is that really what I wanted to say? I'm sorry, I have to assume that x and y are both 2 alpha elder, then I can take anything for y prime. Okay, nevertheless, there is, as you ask it, nevertheless, you can ask that there is a notion of x truly RAF. I've not, for the time being, I've not talked about the fact that truly, is there an E in truly? Yes, there's no. Truly. The one employs the term RAF, but the X doesn't have to be a RAF path if interval in AB, the sub of xt minus xs norm E divided by t minus s, the 2 alpha s different from t belonging to E is equal to plus infinity. So we demand that taking an arbitrary, there is no interval on which x is 2 alpha elder, and then y prime, if it exists, then it's pretty obvious. Okay.
Don't you require also X to span somehow the whole space E?
No.
Because if you are contained in the subspace, you will define y prime of S within the subspace in which X lives, and on the orthogonal direction or whatever. You can put whatever you want. You will a bit like it. I mean,
That's correct. But I'm
like alpha in one direction.
You're perfectly correct. And I've been, yes, okay, this is because I was just in 1D. I guess in higher dimensions, you will have to be more careful. Yeah. In 1D, this is okay, true roughness you can define in any circumstance, and the y prime is unique if it exists in the 1D case. Okay, you're perfectly. And as an exercise, for those of you who know Brownian motion, is truly RAF. Yes, that's correct, yes. Okay, so you're perfectly right. Now that we have this concept, we can generalize a little bit the definition of RAF integrals. Okay, so I should quote a few properties. Before I move on, I should quote 2 properties. So of course, there is a rule that if you have, I will not write down all the details, but if you have this and these 2 are controlled, then there is a control also. There is linearity, obviously. The Gubenelli derivative has nice proper familiar properties. Then y prime plus lambda z prime is going to be a control. If y prime z prime are, and then there is a real number. And you also have the product. Y z prime plus y prime z. Okay, so yes. And here I write it only in 1D. Here, obviously, it makes sense for anything. Here, I would have to look at a bilinear form or whatever with continuity and all that, and then, well, I could formulate this also. It would work as well, but it's a bit more complicated. And one which is not totally obvious, but which is easy nevertheless, so I will not even sketch the proof, is that if f is differentiable with f prime Lipschitz on the range of y, and again I restrain to 1D, then f of y, y prime f prime of y is a control. Also, this in principle could also be formulated in more dimensions, but I will not try to do it. And the last one is the chain rule. And for that one, we can, so you imagine this time that this time y is from AB to F, Z is from AB to a certain space G, and then you imagine that y prime is a control by X, and Z prime is a control by Y, and then the conclusion is that properly understood Z prime Y prime is a control by X. So this is really the usual chain rule, and it works in. You don't have to think. Well, it works in any dimensions. So in the case, okay, so just to be sure, in the case of infinite dimensional spaces, I would also insist that each of these guys be continuous, a continuous linear map. This is the case of these are continuous linear maps. And then this is this here is just the composition. This one takes you from E to F, and this one from F to G. So indeed, this takes you is a linear map from E to G. Okay, so these are very simple properties that you can check for yourself easily. Now that we are equipped with this, we'll move on. Well, I still have a lot of homework to do. We can move on to graph integrals. Imagine that x is a graph path and imagine that y prime you have alpha, and you can think of alpha being in 1/3, 1/2. Where if I'm a control y by x, and then you define the what I call Riemann sums, and to be explicit, let us denote them by y prime, and this by definition is so delta is a subdivision, tagged subdivision, right? And you take this sum, and this is as expected. So we are going to take the first order approximation. So this is going to be yt 2m plus 1 xt 2m plus 2 minus xt 2m plus y prime t 2m plus 1 tensor the identity on E. We shall see why this is the way we should let it act the way we want. And then you have the blackboard P 2m plus 1 P 2m plus 2 minus x 2m plus 1 P 2m, and easily seen that these are gamma Riemann sums. For gamma st, you won't be surprised. I'm sorry, here is the tensor product. Ys tensor xt minus xs plus y prime s xst. Okay, so this is the definition. And then we say that, and another definition, we say that integral a to b of y d, and then I should use exists if the Riemann sums have a limited small mesh. Okay, and now the basic result is the following. Gamma is triangular with exponent 3 alpha. We can view this as a lemma or whatever. If alpha strictly larger than 1/3, then integral AB. Yes?
Gamma is one to use tensor product, it should be the y, again, it should be y prime s tensor identity.
Yes, thank you. So it acts, we let it act on the first component. exists by the Turing lemma. So the only thing we have to do is to check that gamma is triangular with exponent 3 alpha, and then if alpha is larger than 1/3, then 3 alpha is strictly larger than 1, and so we have that the integral exists, and we don't have anything to do, anything more to do. This is really, this computation is easy, and then this is a consequence of the Turing lemma, and we have our integral. So will I give the proof? Well, so first of all, so just to give a, well, I will not do the details, but it's, I let you check the following, that if I look at, so first of all, gamma is reduced, gamma TT is identically equal to 0. The fact that this relates on the fact that XTT is automatically equal to 0 when, and this is a consequence of chain relations if you think about it. But it's not, okay, that's obvious, so it's reduced. And then if you compute gamma. In which order do I do it? Gamma ST plus gamma U minus gamma SU, and then it's easy to see that this is simply, I will define RST in 1 second. Where RST, this is simply equal to YT minus YS minus Y prime S XT minus XS. And so it should do the right job if I'm correct. So I guess this deserves, am I correct? Yes, this deserves a tensor product. And this is, so, and to get this little identity, use chance relations. And now you see this guy here, by hypothesis of a control, this one is of order 2 alpha, this one is of order alpha, so this is 3 alpha. This one is of order alpha, this one is of order 2 alpha, so this one is also of order 3 alpha, so we've got the 3 alpha. So if I just put things here, this is 2 alpha, this is alpha, this is alpha, this is 2 alpha. And now, also, one very important thing is the following, that in fact, and we also have, so the integral exists, and then there is one third point, which is the Raff-Young-Love inequality. Now I'm wondering why I'm writing Lover in that way. Should is it correct to put this and nevertheless add the E? I don't know. Okay, anyway, so it's you can correct, and I will try to clean things in the notes. And the Raff-Young-Love inequality is the following: that integral AB YU tensor D. Okay, so again, here, of course, I should tensor product XU minus the approximation. So this is gamma AB. I don't want to write it again in full. The norm is the appropriate norm on the tensor product F tensor E is less than or equal K divided by 1 minus 2, 1 minus 3 alpha times B minus A is 3 alpha, and K, you see this gamma is in the same space, so K is such that gamma S U minus gamma ST minus gamma TU. This is in the same space, F times E is less than or equal to K. What I call the notation, I remember STU to the 3 alpha. So I have my space here, I use it to define K, and then whatever, I can try to find the best K I can, and then I can put it there and get this inequality. And you can refine a little bit. You can typically gain a factor 1/2 or whatever on K by doing some optimization. But anyway, what is important is really not the constant, is the fact that this bound exists. Yes. Sure. Thank you. So let me note, so this is the notation integral dy, I'm sorry, y times dx is ambiguous. Because y prime is not mentioned. Okay, so when you write down such an expression, you have to make clear what you use as a y prime. This is ambiguous. And very often you don't even you write it dx and that's the boldface x, and then also you have to keep in mind which blackboard x you are using.
You show that the control y prime is not unique.
Yes.
Does the integral depend on which control you choose?
It can depend. There are certain circumstances in which it doesn't, and sometimes it depends. So you have several controls, and the integral in the end depends on the control. Sometimes it doesn't, but in general it does. So really, it's important to most of the time it's from the context that you know which y prime you are going to use, but in general you should make it clear. Yeah, okay. And we are going to see just an example, in fact, immediately, I guess. Okay, so I propose a little exercise, which is, well, if alpha strictly larger than 1/2. Why not? Then RAF dx and young dx lead to the same integral. So which well, so it can be that in fact I've not done it. Maybe I should. Did I mention that? I'm not sure now. In fact, if you imagine that alpha is larger than 1/2, there is only one possible blackboard x, which is the Young integral. I think I mentioned it at some point, or if I didn't, I should now. There is only one x, namely x st equals integral from s to t of x u minus xs dx. U, this is à la Young. This is, well, this is, it's easy to prove, in fact. So this is the little exercise. And now there is something which is somehow, well, crucial or not, I don't know. So, minimal example. Y is a constant map. Y prime equals 0. Then the rough integral a to b of y dx is equal to y little y xb minus a. And in fact, I don't see any, if x is too regular, I don't see any good reason why this should not depend on the choice you do for y prime. So this is maybe an example for Jeremy, when you can have a dependence. I didn't try to check if things would change if I would change another, but I guess, well, there should be some contribution, isn't it? And then almost minimal example. I imagine that y is equal to x, y prime is equal to the identity linear map on E, and then retarded, advance would be the same, retarded rough Riemann sums are telescopic due to Chen. And the result is that, in fact, so the retarded Riemann sum along delta of what I call x X identity E, it's easy to see that if I made no mistake, this is just going to be XA times XB, the tensor XB minus XA, I'm sorry, I'm not talking LaTeX, plus X AB, and this is true for any subdivision. It's just, you see, this is just one of the sum. If I look at the summons, or if delta is the trivial subdivision, this is exactly the value of gamma. And now, whatever the subdivision, it's telescopic, and what you get in the end is that you can, it's Chen's relation, really. So then this tells us that integral a b x insert d x is equal to, if I make no mistake, well, I just wrote it, so it's xa times xb minus xa tensor plus xab, and maybe more to the point, if I put the two together, integral from a to b of xu minus xa d xu, this is going to be xab. So this is a little computation, and somehow it's reassuring, you see, because when we started, so it's just to make a comment, x is badly irregular, then integral from a to b xu minus xa times dxa is meaningless. The idea of rough path, use an x as a substitute. So morally, we would everywhere we would write down this meaningless expression. We would replace it by x, and in the end, x is indeed. You find that now both sides are defined, and then x is exactly equal to the integral. It will be x. Dx from a to b. So I'm sorry. Xu minus xa tensor u xa. So you see, the theory we've tried to explain indeed gives something reasonable in the end. You have something you don't know how to define, you introduce a new structure. This structure allows you to define integrals, and then in the end, when you compute the integrals that are well defined, you find what you expect. But, this one is meaningless, but in the end, we have a meaningful expression. We really compute it honestly using Riemann sums. Okay. So now we are going to do something that revolves around a question that you raised. I don't remember who raised it, but, which is the following. So, well, maybe I should call this, it's a new section, it's lifting to a rough path. So I mentioned this theorem saying that every path can be lifted to a rough path, morally. But here we are in a better situation. We already have what? So we have x, y prime. Is there a natural the question is, can we construct in a natural way a y, and also integral rough integral? And the answer is yes. And there are many ways to see it, but in fact, I will just give you the result. Which is simple enough, and it looks, essentially, this is, well, in fact, there is a simple and usual differential geometry behind this formula, but the point is the following. So imagine that you define, so I'm using many times the notation gamma, but it's every time for something different. So imagine that okay, so we introduce Z that goes from AB to G, and imagine that Z prime is a control by Y. Okay? So if we are in this situation, once we have a natural candidate for this guy, we can compute this integral. And the main point is the following, that gamma st, it's zt tensor yt minus ys. So this is, you see, this is the first part of a gamma you would imagine. It's just the first order approximation for an integral. And then you give yourself an object ws x st. This is a bit long to write, so that's why I choose this. And then if ws is defined to be z prime s, well, there is tensor 1f, y prime s, tensor y prime s, and x st, gamma st is triangular order 3 alpha. And so check, and that's again, I mean, that's just algebra. And the chain relation is completely crucial. So I take this out of my hat, of course, but you see that in those, this is the first order, zeroth order term, let's say. It's first order in alpha, so this has typically alpha. I'm sorry, here, this one we don't need. This one is of order 2 alpha. So if this guy here is reasonable, this is indeed going to look like a Taylor expansion where this is a zeroth order term, and then this is the first correction. Then if you compute that gamma is triangular, you apply the Sewing lemma. So the check is easy, and you just have to make a little computation, and the details will be in the notes. And then by the Sewing lemma, integral a to b of delta gamma exists. So we have found something which is, you see, that's something nice. We have found something that starts like the computation. This is the first part of what should contribute to integral of z dy. Here is a correction. And the correction makes the whole thing regular enough that you can compute the integral. Okay, so the first thing we can do with this example, special case.
Blackboard Y.
There is no blackboard. I don't need any blackboard white for the moment.
You can define it
That
well.
is your question. So
Yes, that's what I'm coming to. That was my question, and so special case. Well, a stupid special case is when z is equal to y and z prime is equal to 1f. And then you get a certain integral from a to b of delta gamma for this special case. So maybe I should, I'm sorry, maybe I should take some notation for that case. Yes, I take some notation and I write down gamma I've tried to make all the notations, so here it is. I have y, and of course, if I were really, okay, let me put it. It's not in the note, but let me put the y prime just to be totally explicit. So I just explicit what I call gamma there in that special case, and this is simply ys tensor x yt minus ys plus y prime s tensor y prime s applied to x st. And then with this I can, so I apply the lemma, and so what I get is integral from a to b of delta gamma y prime x. Okay, now what do I do to this? I subtract y a y b minus y a, and I define it to be y a b. Okay, this is my definition, and then name y is a rough path. So so the point is that so why is it so? The reason is easy. In fact, we have to change relation. Now we already know that if you take this as a candidate for, that's something we saw very early. If we take this as a candidate to be Y, the chain relation is going to be fulfilled, but it doesn't have the right regularity. Now this guy here satisfies chain relation, so it makes no contribution to chain relation. So this here tautologically satisfies the chain relations. Chain relations is tautological. And regularity is the Young-Love estimate. Okay, so we've succeeded in constructing Y, which is in some sense canonically associated to the situation. And then, of course, we can use this Y. And what I claim now is that, in fact, I'm coming back to this notation. One can show that, in fact, this is equal to integral from A to B . So you can check that so, which means that to say it differently, this means so it's y s prime tensor y prime s x st and y st do the same job as counter terms.
I don't understand. ZS is not Y.
Well, this was for a special case. The special
that
case
is
here. This was for the special case. Now we return to the general Z. To our favorite gamma here. And so you see these two objects here are not, well, these two things here are not equal. However, their difference at small scales is small enough of order 3 alpha so that you can use either of them to compute the rough integral with respect to y. Either, yes?
Because I was naively expecting that blackboard y would be y prime tensor y prime. So why doesn't it work? It does not satisfy chain relation, or it's...
Yes, it does. I guess it doesn't satisfy chain relations. Yes.
Okay.
But what is the rough path bold YS in general?
It's, well, I decided to take it as that one.
So what is Z? Is the Z of the special case?
Z is anything that is controlled by Y.
Okay.
Big Y, and then you use it.
Okay.
So you see, so there is some flavor of universality somehow, or whatever, that tells us that you can use. If you view this as a counter term, in fact, only the dominant singularity somehow contributes to the definition. The lower order terms don't. Okay, so what I suggest is that I finish what I wanted to say about this topic, even if I've been a bit long, and then we make the break, and then when we resume, I will. This will be funnier. hopefully. So let me just conclude. Okay, so now you will find it in the notes. Once you've defined an integral, of course, you don't want to compute integrals by returning to Riemann sums. So you need to have nice things, and you have the fundamental theorem of calculus, you have a change of variable formula, you have the product formula, and all these can be defined for rough integrals and proven. And this will be in the notes. I don't have time to do it and even to write it down. It's essentially what you would expect, plus some corrections which look like, well, which look a little bit like what you see in stochastic calculus. So there are corrections, but it's just easy. I mean, if you work blindly without asking, well, making the estimates to show that you are right, you just can do things blindly, and well, it's easy. And then the proofs are not very difficult. But then there is so let me mention it. There are useful extensions. Of all the usual rules for integration. Fundamental theorem. Product. Well, integration by parts, let's say. This is a better way to say it in this, okay? And then change of variable. I don't mention it. What I would like to end with for these technical stuff is we started the first lecture by asking questions about what do we do when we want to solve controlled differential equations, and I would like to show you that we made a small step towards that, and this is based on the following remark. So maybe I should call it 4. What about graph controlled differential equations? And the remark, there is a basic remark, which is that Young-Love says that if I define zt to be equal to integral from a to t of ys tensor, well, dxs, then zy is a control of z by x. So so y is the Gubinelli derivative. Is the or a Gubinelli derivative. Z with respect to x. So this looks like this looks quite intuitive, isn't it? It looks good. Okay, so now from now on we assume that d is equal to 1. And we ask about dy is equal to v of y dx on AB. And So one thing we can try to do is to turn it into an integral equation. So this would say that yt is equal to y a. Let me take the initial condition. Let me write in small letters, plus integral from a to t v of ys d s. Is a possible interpretation. Now we are not already safe, because for this to make sense, this should be controlled by x, which is complicated because we don't know where we don't know. If I input any y there is no reason that it's going to work. So as such, the meaning is unclear, but at least we have Picard iteration, and that's what I would like to conclude with. So you see, this is not very deep. I mean, the point is the following. So we start with y0 is just equal to ya on ab, and then I define y n plus 1 t is equal to ya plus integral from a to t v of y n s d x s. And I just want to show you in a very simple way, and okay, I do this, and now I have to make some assumption. V is differentiable on R with Lipschitz derivative and then it's easy to see that the recursion step is working. Imagine that imagine that yn, so first of all, y0 with 0 is a control of y0 by x. And then, okay, so that's the first step. And now imagine that yn is defined, is controlled by x. And that's all, I guess. Is defined and controlled by x. Well, then, because of the properties of V, then V of yn, and then yn prime, V prime of yn is a control of V of yn by x. Okay? And so fine. So integral from a to t V of yn dx is defined. And by the Young-Love by Young-Love. This is defined and is controlled by X. And so we infer that in fact, because yn plus 1 is defined by this formula, this is controlled. I add a constant, so this is also controlled. And so I can input go to the next step. And to conclude, if I understood correctly, I'm not totally sure, but okay, this is a bit technical for me. But in fact, to have convergence, one needs more. V should be that V double prime is Lipschitz. So V should have two derivatives, and the second derivative should be Lipschitz. And this is also a condition for uniqueness of the solution and well, for me, it's not totally obvious to decipher that really you need the second derivative, and also uniqueness is something where I have a little problem with. Well, let's say maybe if X is truly rough, so you don't have the choice for the binary derivative. At least X is truly rough. So well, if you remember your young age, which for me is very far away, but maybe not for you, even for the case of standard Picard iteration makes sense for continuous function. When V is a continuous function, that's pretty obvious. However, to have convergence of the Picard scheme, you need the Lipschitz. And so you see, you need one degree of regularity more, and this is essentially the same here. So intuitively, to have uniqueness of the solution or to have convergence of a Picard scheme, you need one more degree of regularity than what you need just to have the Picard scheme well defined. So I think I should stop here, and we resume at some point. And this should be more fun, less technical at least. I don't know. Maybe that was already fun, but it should be less technical. See you.
Break.
Vous montrer un ou éventuellement deux exemples, mais probablement juste un du temps qui reste, d'apparition naturelle de chemins rugueux dans des choses qui ressemblent un peu. Oui. Oh, thank you. So the idea is to give you at least one and maybe two, if time permits, examples in physics where rough path theory makes sense. And in fact, okay, let me say, I will do things in the opposite order than what I expected. And I will give you the one which is really relevant for physics. I will say very few things about it, but it's nevertheless, I want to read. So it's, let's say, physical Brownian motion. I will just say a few words about it, but in a magnetic field. And this will be really sketchy, but one of the ways to describe physical Brownian motion, if you remember, or if you don't know, I remind you, you imagine you have a particle of mass m. This is the mass of a particle. And you write down a second derivative, and you say that you have some friction, so you have a certain, let's call it gamma. This is friction. Plus, where did I, okay, so I did it very naively. So this is, and this is Brownian motion. So the most naive version of Brownian motion given by Einstein was that, in fact, the motion of a particle submitted to shocks in a colloid suspension, for instance, is Brownian motion itself. And in fact, it doesn't, well, you can do many interesting things, and surely Einstein did. But in fact, for physics, it's really better to go one order more and to say that it's not the position of the particle which experiences a Brownian motion, but it's speed. Okay?
Est-ce qu'il faut que tu m'ailles là-bas?
Yes, I do.
On est dedans, mais...
No. That's what I wanted to do. There was room for it, but that's what I wanted to do. Thank you, Kira. So, so in particular, here, if you define m x dot to be equal, as we would expect, to the momentum, then the momentum itself is going to be up to a scale of Brownian motion, essentially. Oh, I'm sorry. It's an Ornstein-Uhlenbeck process. And the reason why is easy to see, is that if you write here, you get that P dot is minus gamma divided by m. P plus B dot. So this is Ornstein. And you can wonder what happens when m goes down to 0. So there is an important friction. The friction is fixed, and you let the mass be very small. And then something interesting happens. P goes to 0 in a certain sense. And x becomes Brownian. And when I say in a certain sense, but P is of order m to the 1/2, not m. To say this is a bit a slightly vague statement. There is an anomaly, of course. If you look at this and I say, okay, let m go to 0. Well, okay, there is a factor m in P. So, but when you let m go to 0, due to the properties of the equation, in fact, x dot starts to be more and more irregular. And in the end, the rate of convergence of P to 0 is m to the 1/2, not m. So there is an anomaly. Okay, so this is the standard theory. It's not. By the way, if you solve this equation, there is so this can be solved. This is just a side remark. By Young integration theory. of course, there is a Brownian motion here, so you could do it by stochastic calculus. But in fact, you see, B is essentially 1/2 Hölder. When you solve this equation, you see you just have to look at the variations of B retarded by an exponential. So you solve it by a variation of constants. So you have an exponential behavior, and then in the end, I will do it wrong if I try to do it like that on the blackboard. But essentially, in the end, what you get, so someone will correct me, I am sure. So what you get is P(T) is equal to e to the minus gamma over m t, P0 plus integral from 0 to t e to the gamma over ms dbs. Yes, that should be something like that. That's what you find. And here, of course, you could do it by stochastic calculus because it's a stochastic integral and it involves Brownian motion. But in fact, there is enough regularity that this, you see, this is almost 1/2. This is 1 Hölder. So Young theory gives you plenty of room to say that this can be defined really pathwise. And just to make one more aside, in fact, you see, now we have Riemann, we have stochastic integral, we have Young, we have rough integrals, whatever. And in many circumstances, a number of them are defined simultaneously, and there is a little work to do, but every time they have to coincide, they do. But it's a little work you have to do. Even because well, it requires a small argument to say that the stochastic integral and the Young integral are the same, but they are. But anyway, but the point is that there is this small anomaly that you can see already in this formula when you let m go to 0. In fact, you cannot apply. It would be correct if Watson lemma would apply, but Watson lemma applies only when the integrand is regular. It doesn't. Watson lemma doesn't work, and there is an anomaly. Now, instead of taking gamma as a friction constant, imagine you are in the multidimensional. Take gamma as a matrix whose eigenvalues are with positive, I'm sorry, real part. Okay. So then you can do, well, there are many things you can, the theory carries over. And in fact, for instance, take t equals 2, and I will have the basically everything wrong, but nevertheless, and let's take here minus so did I write it down somewhere explicitly? I'm not so sure. Okay, so take d equal to and rewrite the equation now that as in 2 dimensions, so that this is equal to minus lambda dz over dt plus dw over dt. So this is our Brownian. We have a complex notation. And lambda is equal to, how should I say it? gamma, this is really the friction. And if you write the other, what remains as HQ, something I call H3, you will understand why in a second, then it turns out that this describes thermalization of a particle in the xy plane z is equal to x plus iy without surprise, but of course with a transverse magnetic field. H3, and Q is the charge. So this is precisely this is a way to embody in 2 dimensions the wedge product of QV times vector cross product with the magnetic field. Okay, so now you can have fun and study this equation. And just to say things very briefly, what happens when m goes to 0? And in fact, things are as before. If you define P to be equal to m dz over dt, and just to get my notations right, I said Q equals lambda z, and then what you find is that I write it now in well, as a mathematician. So I have dpt is equal to minus dqt plus d double dt, and dqt is equal to eta divided by tau pt dt, and I have made a small change of notation. So tau is just a time scale. It's m divided by the real part of lambda. It's a time scale. And eta is tau lambda divided by m, and it's a complex number with real part 1. This is a way to rewrite things. And so now what you are going to do is to look at tau goes to 0, in fact. And you can do many things, but the point is that when tau goes to 0, P goes to 0 as tau to the 1/2, and Q goes to Brownian motion. But you see, of course, this doesn't apply very well, but as you all know, imagine that you are in a regular situation when you have a particle moving in a magnetic field. It just makes circles, and the circles have a size which is inversely proportional to the speed, or to the square of the speed, or whatever. Well, anyway, so you may expect that something is going on here, because due to the magnetic field, the particle is going to make circles. So if you compute the area spanned by the particle during time, there is no good reason whatsoever why this should be small when when you go to when you let the time scale go to 0. And in fact, The next result is that Q and the area, so it's going to be I should write it down as a vector if I want to do things properly, and then integral of Q dq bar, Q bar dq, Q bar dq bar. Goes to a certain limit when tau goes to 0. This goes to Brownian. Brownian bar. And the non-trivial B, a non-trivial first path, which remembers the area swept by the Brownian motion, by the particle motion due to the presence magnetic field. This B in fact, it's going to be what you would call the integral, and you would put B dB bar, B bar dB, B bar dB bar. This is Alaito, in fact, Ala Stratanovich, in fact. Ala Stratanovich means that integral of bx dbx is equal to bx squared divided by 2. I write it. I don't. There is no additional. Term, if I'm correct, plus I t minus s 0 1 minus 1 0, and of course I'm missing something which has to do with the parameters that survive in the end, and also there is somewhere I should see the. I guess it's going to be eta. You have a question?
You should see the magnetic field.
Yes. And so eta should be somewhere, and where is it? I'm in trouble now, so I guess so. Let's say that I wrote formulae which are too general, in fact. So I'm in some trouble to get.
Michel, when you say that you wrote bx dbx you get bx squared, so only the same for y, but when you have cross one, it's 0.
Yes, it's 0. Yes, it's 0. Yes. Well, no, I'm sorry. The expectation is 0, but the integral itself is non-zero. That's okay. So okay, I will make a comment on that. Yes, so there is yes, indeed, there is a random part. So I will comment on that. So let me try to find where the eta is hidden. I'm sorry. So here is eta. Here is eta bar. I'm correct. So okay. So take this formula with a grain of salt. It will be correct in the notes. But so there is an anomaly definitely, and there is a non-trivial half path in the end. So this is one of the examples where half paths appear in a natural way. And if you think, for instance, that you use imagine you use this physical Brownian motion in the magnetic field as a source for another object, and you look at the limit when the mass goes to 0, then just as what happened for the very simple example we had, the one with the the particle which was just circling without moving around the center. This was the example of the minimal example of half path I gave you. This is going to have an influence on the limiting behavior also. So it will play some role when you solve differential equations related with when Q is a source. In the small m limit, this will leave some remnant of the half path structure. Okay, so this is
When
yes.
the magnetic field vanishes, then you don't need to have any correction.
No,
So
definitely.
it means that the coefficient should be 0 when the magnetic field vanishes. And it's eta minus eta bar or something like that?
It's yeah. Don't ask. It will be correct in the. You're right. It should definitely vanish.
It should be the imaginary part of eta or something like that.
Yes, but then okay. So but maybe maybe that if you put eta here, then this one is the ito, and when you put the real part, the real part, then it's not okay. So I'm lost now because my notes are not properly written at the moment. So but there, okay, there is. So I would like to end now with something which is an even simpler process.
To conclude, so the effect of the magnetic field is this.
Yes, there is an anomalous law, and essentially the thing that the thing that remains that is non. If you look at, so this is defined using stochastic integrals. This is the process. In fact, okay. So just for history, the integral bx dby minus by dbx. We put a 1/2. This is called. This was defined by Levy before stochastic integrals, in fact. But in the nevertheless it was as a stochastic integral, and you see this is called the Levy area. And this is called the Levy area. First of all, it has the right dimensions to be the Levy area, but also if you imagine that you have xt, yt, a smooth path, bounding a region omega, then area omega. This is integral of dx dy. Let me put a wedge just to make things the way they should over omega. But this is also the integral over the boundary of omega of x dy minus y dx with a 1/2. So this is one of the standard formulae for areas. And so this is just the translation for Brownian motion. This is the algebraic area that is spanned by Brownian motion when it's two-dimensional Brownian motion. And of course, in average, we expect it to be 0 because there is no way it doesn't work. And this is indeed what it is. And essentially, this guy here is hidden as the imaginary part of that guy. And
this is the example you gave in one of the first lectures, essentially, for the thing circling.
well, this part here is exactly the same, and just you add the Levy area on top of it. So you span the Levy area. Yes, sure. And you can do many beautiful things using the Levy area, and you can in particular compute its Laplace transform, the Laplace transform of the law. So if you look at packages for solving stochastic differential equations with more than one variable, so in more than one dimension, you can do the most naive approximation, and so you just keep the first term. But if you go to the second term, which is what we did with rough path, you need to know the law of the Levy area. And in fact, so that's another point I should make. So in fact, this idea of improving, when you solve stochastic differential equations, improving things by going to the next order, this was implemented long before rough path existed, in fact. But it's exactly the philosophy of rough path. The point is that when you do numerical simulations with Brownian motion, you don't really see the difference between pathwise solution or or probabilistic solution or whatever. Anyway. Okay, so I will now turn to something which is even simpler than this one. And it will be the conclusion. And this is what I call waltzing with Brownian motion. And it's just the following. So imagine you are dancing the valse with your favorite partner. So you're doing it gently over the dance floor. And of course, if you dance perfectly, you will just make a small circle. Your motion will be along a circle. So you will make one step and then another step, whatever. I don't dance the valse very well. But now the point is that your motion is you don't do it perfectly, so sometimes your steps are just a little bit smaller or a little bit longer than what they than the average. There are some fluctuations. There are also fluctuations in the angle that you turn each time you make a step, and so your motion is going to be a bit more complicated than just being around the circle, moving around the circle. Okay, so. And we are going to take a very simple model. Yes. When only steps fluctuate, the angle for each step is the same. And so, so imagine, so I take complex coordinates where the dense floor is a part of the complex plane. So imagine that you start at the origin, so you are Z0 is equal to 0, and you imagine that after n plus 1 steps, well, you are where you were after n steps, and then plus e to the in theta xn, or xn plus 1, I'm sorry. Okay, so theta, I'm going to term. Of course, we could let it fluctuate, but I will just show you some pictures. So kept constant. And this one is random. Okay, So there is no mystery. Well, this is just a very simple example. There is no real mystery in it. But so if you look at it,
Random, but not centered on zero. So
no, yes, random with an average, definitely. No, completely right. Unless you're a very, very bad dancer, usually you do something. In fact, so even if you're a reasonably good dancer, Xn is always positive, but in fact, all what you do is well, the only thing that counts in the end is that the average is strictly positive. So
it's okay for me.
okay for you. It works. So this is a sample. I don't know exactly where this motion started, but you see, indeed, you are doing little circles. But of course, because there is some randomness in the steps, well, it's not perfectly a circle. Okay, and then you can look at you imagine that you dance for a very long time, and you look at it from. Oh, I don't. How do I get to the next one?
The
Ah ouais, je pense que tu peux mettre le focus dans.
Ah, je pense que le focus. Ça il accepte. Okay, so that you look at it. So yeah, you start with this, but if you look at it from further away, that's what you see. And if you look at it from even further away, that's what you see. So definitely there are two scales in this problem. At short scales you see the circles, and at large scales you see something which in fact is Brownian motion. Two-dimensional. You see, it's not unexpected, but indeed, what you get in the end is that you have only one-dimensional random walk, but in the end, what you see is a Brownian motion. Okay, and you can do it. This was done with taking only positive steps, but if you allow for steps which are negative sometimes, it doesn't change much. So this is an example, and if you look carefully, you see some negative steps here, there. This one is maybe the most visible. This one also is negative, but it doesn't change much. And if you look at it from further away, you see just making filling the dance floor somehow. And again, if you look at it from very far, this is what you see. And then this was done for dancer which made a very small angle at each step. But if you make larger angles at each step and you allow for negative steps, you see that this is more irregular. Then if you look at the larger scale, so in principle, well, in fact, I did it by, well, it's just visual, but somehow the zoom is the same for all the samples. But you see, when you go from the first to the second sample here, you don't see really that you've turned into a Brownian motion. But for this one, already at the next step, things start to look like more like a Brownian motion. And well, in the end, that's what it looks like for that piece. Okay. And then you can, well, it's not unexpected at all. You can compute the area that is swept by the path, exactly the same formula as for the magnetic field. Well, you do it in a discrete case, and you just compute numerically. So you imagine that you have a process, let's call it the area, and the area at time n plus 1 is going to be the area at time n plus, let's put a 1/2 here. This is going to be Zn plus 1 minus Zn. Here, let's put a bar. minus, I'm sorry, let's say it's just the imaginary, just the imaginary part. Imaginary part of Zn bar Zn plus 1 minus Z. So you can plot it to see what goes on. And the simple thing that happens is the following. So the blue line is the area, really this formula. The green line is the area when you make larger steps. And basically, you make enough steps that you don't see anymore that you've been circling somehow. So you see it's essentially 0. But if you really look step by step, you see something, and the red line is just the prediction of computations. And you can do it for. So this is in the wrong order, I guess. Yes. So this is in fact the one related to the last sample, and it goes. So you see well, there is this here. This is far from perfect because we are not looking. There are still fluctuations, but in fact, what you can show is that again there is an area that survives in the limit. And what happens for this little process is that if you rescale it properly, so rescale, the standard formula for doing that, you all know that it's.
On tourne tout le temps dans le même sens, quoi. Il y a une aire.
Voilà. I would say there is nothing deep in this story, definitely. Where is it? Where are my little pictures? I don't know. Of course, I lost track of what I wanted to put. But anyway, it's not very important. Well, anyway, the only interesting thing in this example is that in fact, in the limit, so you see what you do to do that somehow. You take a large n and you define a new process Znt, which is I guess it's you have to sigma square root of n over 2. So this is the variance of xn. And in the numerator, I always make it wrong, but essentially you take. Let's do it that way. Let's imagine you take the z at times. What is the right scaling here? I guess. And so I'm sorry. Yes. For instance, you take you imagine you take and you take n to infinity, and you rescale just the way it should, and then what you see is that in fact Ztn goes to Brownian motion. But as before, did I keep it? No, of course, that's what I decided to. But Ztn doesn't go to standard B of Brownian motion. And it's something I don't understand really why, but all the examples I know for that look like that is that in the end you get something which is not the standard B of Brownian motion, but it's the difference is deterministic. That's just, you see, this line here is just deterministic, and you see that there are very little fluctuations, but this is just because the size of the sample is just a few millions. That's not enough to kill all the fluctuations, but in the limit, the difference is deterministic, and the interest is that Z infinite minus B, contains an area part. So there is area swept, but in fact, it also ZdZ is neither Ito nor Stratanovich. Usually, depending on the way you take depending on the problem you look at, when you go to the continuum, the integrals of B against itself, B dB for one component, you find either Ito or Stratanovich, so you find B squared or B squared minus C. And this is one example where, in fact, there is something that happens not only to the area part, but also to the standard contribution to stochastic integrals. So it's a very simple example that you can study really with minimal technical apparatus. It's just computing some expectations of sums. You see, this is really very easy. And in the end, what you get is a process, in fact, which you can think of as an effective model, if you want, of Brownian motion in the magnetic field. Pardon?
The count is a function of theta, which
yes, yes, and again, I don't know it by heart, and of course, I don't know why, but I can give you it. I can give it to you. I'm pretty sure I lost.
La transition, le fait que le verre soit horizontal, c'est juste que la pente est très faible.
Oui. Ah oui, il n'y a pas de transition. Non, il n'y a pas de transition. Il y a pas. Non, il y a un crossover, mais il n'y a pas de transition. Ah oui, il n'y a pas de transition. And one last thing is that you could study exactly the same. You could study exactly the same kind of process directly in the continuum. Maybe I can take that, and the results would be exactly the same if you imagine that you define zt to be equal to integral from 0 to t du plus square root of 2 dbu e to the I u theta. So you see, this is your infinitesimal step, and this is the angle you turn. Well, it needs to can be in the same. And of course, in this problem, as soon as you look at good dancers that make a small angle and are quite regular, you see that there is some area accumulated. But if you look, for instance, at this, I'm sorry. This example here, you still see basically the angle is pi over 10 for this example, but you see there are quite a number of times when you go back, and it's not so easy if you look at large angles and the possibility to make backward steps that arises quite often. Then it's more and more difficult to see that you are going to accumulate area. And here, for this case here, you see at small scales, whatever you could put you can put a coefficient if you want. It doesn't matter very much. But whatever lambda at small scales, this one is always going to win. So let's say exactly if you discretize or whatever, half of the time you go backwards. And so it's not so obvious that you are going to accumulate area, but nevertheless you do, and it's exactly the same. you see exactly the same happening in the end. Okay, so I think it's largely time that I should stop. And I just wanted to thank the organizers very much, because it was a real pleasure, and also the participants, because they were really active and asked questions. So it was a real pleasure for me, and thank you very much.
Do we have some questions?
Yes.
In the room here, no questions. We had a lot of questions already.
Just to answer Vincent, basically this piece here is tangent theta over 2. I don't like it, it's probably cotangent. Okay, probably cotangent. Because theta is very small and the accumulated area is large.
It vanishes for some theta. Trivial one.
Oh, it's for theta equals 0, it vanishes, you're right. So no, no, the smaller theta, I'm sorry, no, it's theta over 2. It will be clean in the notes. What was the question?
No, okay, so thanks, Michel.